The Nexus prototyping board we're using contains an Artix 7 FPGA. In this video, I want to briefly summarize its physical capabilities and how it relates to memory. In order for you to get any information about this particular series, what you need to do is you need to go to the documentation site on Xilinx. And what you can see is that it actually has a ton of documentations. There's about 118 documents. You can actually sort through them between application notes, white papers, and user guides. Generally speaking, I refer to the user guides, which are basically about 14 documentations. And most of the information in this video comes from these documentations. Okay, so let's go back in here. Okay, and we're gonna start by talking about a general FPGA or a generic FPGA. And as it turns out, that an FPGA contains a 2D array of what we call logic cells, and sometimes we refer to them as LCs. Some other manufacturers might call it logic elements or LEs. Okay, we're gonna just refer to them as logic cells. So these logic cells, without going into the details of how they're constructed yet, they can actually implement either a combinational circuit or a sequential circuit. Okay, and then what you do is you can use multiple of these logic cells to implement different logic, whether combination or sequential, and then you do have between them what we call it a programmable interconnect. And this programmable interconnect, you're going to see they're basically programmable switches that Vivado strategically knows when and how to actually connect or disconnect certain things. So let's assume you're constructing some sort of a circuit, and the circuit, you cannot fit everything in a single logic cell. You're going to actually use a multiple logic cells, and these interconnect will be strategically connected or disconnected so that it routes certain inputs and outputs between these logic cells. Okay, so Vivado does this for us. We haven't been doing it ourselves manually because Vivado does it. That's the purpose of Vivado. This is what it's doing when we're doing synthesis and implementation. And now, to just take a look, brief look of what's inside one of these logic cells, what you can see, it consists usually of what we call a lookup table in here. This lookup table, similar to RAM, we can use it to implement configurable combinational circuit. And in an Artix 7, these particular lookup tables, generally speaking, they can be used as a 6-input lookup table, or 2, each one of them is a 5-input lookup table. So you can actually configure it either way. All right, and at the same time, you're going to see that inside this logic cells, there's a flip-flop, and in the Artix 7 particular family of FPGA, it does have 2 flip-flops. And of course, the Artix 7 also has a multiplexer in it, and it's actually they call them wide multiplexers, and they're usually used for efficient utilization. And there's something that you don't see in here, which is basically also, it has a very high-speed carry logic, okay, carry logic. And that carry logic usually is used when you're doing some arithmetic operations and you want some carry out or carry in and so forth. And it's not shown in here. So the Artix 7 has a bunch of these in here, and you can actually go, if you go to the documentation, you can see more about each one of the construction of these logic cells. So you can see that these logic cells, you can configure them for example, if you want a completely combinational circuit, you just basically use the lookup table, and you just basically route your output completely out. If you do not use a flip-flop, as you probably know, you don't have a sequential circuit anymore. If you need a sequential circuit, you do this as the combinational part that specify the next, for example, the next logic. And this one here is what save the state or whatnot. And you might need several flip-flops, so you're going to use different logic cells. So what you see is that we can implement memory just by programming these lookup tables and the flip-flops and using them. However, as it turns out, this is not a very efficient use of the logic capabilities of an FPGA. So as it turns out, that the FPGA doesn't only contain logic cells and programmable interconnects in here. What it does, it has something else, we call it macro cells, that are not shown in here on this particular figure. The macro cells, what they do are, they're not FPGA, so they're basically not reconfigurable. You can't reconfigure the logic or program them to do whatever you want. What you can do with these macro cells are dedicated ASIC. They're dedicated for specific functionalities. So you can see that these macro cells, we're going to see some macro cells are basically memory blocks. They're already pre-implemented memory. It could be static RAM, DRAM, whatever it is. They're basically they're basically thrown in between these logic cells, so you can use them if you needed the memory. Also, you can see some of the macro cells with the Artix 7. You're going to see that it has combination of multipliers. If you're doing some multiplications, why would you implement it yourself and use some of the logic? So it's already there for you. So you can actually use multipliers. These ones in here, you can configure them to do whatever you want. But sometimes, because certain things are really common, you're not going to program it to be a multiplier if you already have a multiplier in here. So you can actually save some of the logic, the free logic that you can actually for other functionalities. Other macro cells, you're going to see clock management circuits, analog to digital, for example. You can't do any analog in here. So in order for you to use something from external analog inputs to the FPGA, there are macro cells that deals with that. Actually, some FPGA might have a complete processor as a macro cell, maybe several cores of them, like an ARM Cortex, for example, A9 or something like that. So before we move on to further, I want to talk a little bit about the Xilinx nomenclature. So what we have seen is we've seen logic cells. However, if you look at the documentation for Xilinx, you're going to see some references to slices or configurable logic blocks. Sometimes they're called CLBs. Okay, and they're basically just reorganized for flexibility. So you can see that if you have 4 of these logic cells are combined to form what we call a slice, okay? So you call them a slice in here from 4 logic cells. So you have a logic cell, another logic cell, and a logic cell in here. And what you do is you have a couple of these slices in here, and if you have a copy, for example, we paste it again here, and this particular 2 slices, what we call is a configurable logic block. For example, just to see in here, this table comes from this particular series, the documentation. You can get all this information by just taking a look in here, and you can see the lookup tables and the type of RAM it has and everything in it. Take a look at these, skim it, and you can see a lot of information. So what I will do is I'll just talk briefly about one of the tables on this particular documentation in here. And this one here, the Artix 7 is a family of FPGAs. So the Nexus that we are using nowadays, it's either A7-100T or A750T, and the difference between them is its capabilities in terms of FPGA, in terms of logic. Both of the boards have the same types of inputs and outputs. Also, Digilent, which generate or manufactures the Nexus, also manufacture a different board, which is called the Bases. It also has an Artix 7, but it's a little bit less powerful one, and it has less inputs and output. We use the Nexus because it has more switches and more inputs and outputs, or more IOs. So if you take a look at the 2 in here, the distinction, just so that you see it, these are all 7 because there are 7 Artix, okay? Some 100T, some 200T. What you're going to see is the differences between them is slices. So technically, the difference between them is how many logic cells they have. So we know a slice contains 4 logic cells. So if you multiply this by 4, you can figure out how many logic cells you do have in here. And we know that each one of these logic cells has 2 flip-flops. So if you do this about 15,850 times 4 times 2, you're going to get the number of flip-flops in here. And you can try it at home. You can get that exact number. Okay, and these slices, as it turns out, that you do have 2 types of slices. One is called slice L, and the other one is slice M. And the M, it turns out to be that you can use it for a certain type of memory we're going to be briefly mentioning. And of course, we have how many 6 input lookup tables? You have 63,400. And this you can get by basically 6 input logic lookup tables are basically referring to how many logic cells we have. And you can get it just by multiplying the slices times 4 because each one of them has a logic cell. So this is the number of logic cells we have. So if you take a look at the differences between the more expensive one and the cheaper one between the Nexus, you can see that you have almost about double the amount of logic you can actually fit on the Nexus, the more expensive one a little bit. Okay, so in here you do see that you have something called distributed RAM and shift register. So let's talk briefly about it. So as it turns out that the Nexus has 2 types of RAM on it. You're not programming RAM using the lookup tables and the logic. So if you want to actually use something a little bit more efficient as opposed to programming and using these lookup tables, the ones we have, you can absolutely use these lookup tables to implement ROM and to implement whatever RAM you have by just configuring them and letting Vivado connecting different logic cells together. But that basically takes some of your logic capabilities on this FPGA board. And as it turns out, that we probably are better off using some of the macro cells that are pre-dedicated for a specific functionality, which is the memory. So in Xilinx, it has a couple of types of memory. You can have something called distributed RAM and block RAM or BRAM. Okay, so distributed RAM, as it turns out to be, and you can see it in here, that Artix, if you're using the 100T, can actually have a 1188 kilobits of RAM. And it's actually constructed from the lookup tables, okay? And it's usually competes with the normal logic for resources. And generally speaking, it's asynchronous because, as you probably know, lookup tables are just basically, there were no clocks in it. And it's only available for Xilinx. So this is why we're not going to be using this distributed RAM in this course. Okay, because it's not portable. Like if you go to a different FPGA, you're not going to see something similar. Okay, what we're going to be focusing on are block RAM, and block RAMs are usually prefabricated as macro cells. So they're outside the lookup tables. They're outside the logic cells. They're completely separate from these logic cells, and they're generally speaking, they're macro cells that are prefabricated to be RAM, and they're also pre-wrapped with synchronous and configurable interfaces so we can actually use them. So we can use them with clock, so you can actually just use them as a normal clocked RAM. And you're going to see them in most FPGA devices. They might not be called BRAM, but it's like they might be called differently, but they're basically specific ASICs that are thrown between the logic cells, and you can use them as RAM. Without actually affecting your capabilities. So you're going to see that all your lookup tables will be available to you to do some logic in addition to the RAM. And that's what we're going to be doing. So talking a little bit more about these BRAM, what you can see is these BRAM in terms of sizes, each BRAM macro cell, each one of them, we have multiple of them, actually have 32 kilo data bits. Okay, so 2 to the power 15 data bits. These are bits, not bytes. Okay, so you have about 32,000 bits available to you, a little bit more because you need to multiply by 1024. Of course, you can also use some 4K for parity bits if you want to basically do some error correction. We're not going to go into that, but generally speaking, this BRAM can have 36 kilobits, and that includes the parity bits. We're going to just ignore these parity bits in the next calculations. Each one of these macro cells it's reconfigurable, so you can arrange that type of memory. Remember, it's like we have depth and width for memory arrays, so you can either basically put them as a 32K by 1, so you have 32,000, each row is exactly 1 bit, and that's basically, you can see, it's basically 2 to the power 15 times 2 to the power 0. Okay, each one of these rows is 1 bit. You can maybe split it in half. Instead of 1 bit rows, basically your word was gonna be 2, and of course now you have 16K times 2. And you get the idea. You can actually reconfigure it the way you want it. And there are multiple configurations. You can go all the way to 512 rows. Each one of them actually contains 64-bit words. The Artix 7 that we're going to be using, it can actually, each BRAM can be partitioned into 2 independent 18K. So you can, like, if you have completely separate RAMs, for some reason or another, you have 2 different systems, you need 2 different RAMs, 1 macro cells can be split into 2 and used accordingly. So you don't have to use all of them. You don't have to manually specify whether you need half or 1 or 1.5 or whatnot. Vivado will figure this out for you. Later on in a different video, I'm going to show you how we actually specify that I want to use a BRAM for my RAM. So the Artix 7, the one that the 100T that we're using, actually has 135 of these macro cells. Each one of them actually can be configured this way. So 135, each one of them is actually 32 kilobits. So the total available memory that you have is 4,320 kilobits. Of course, you can go in here and you can actually see these memory resources on this particular FPGA, and you can see even this particular documentation will also talk about distributed RAM if you want to know more information about it.